Hello, this is our video for the Discrete Mathematics project assigned by Professor Manish Gupta. In this video we are going to review a well-known algorithm, PageRank. Although it's not used nowadays, it's considered to be a very important algorithm in the study of mathematics. This algorithm was developed by Larry Page and Sergey Brin as their research project. What this algorithm does is that it ranks web pages from the web network, and on the basis of these ranks it shows the pages with topmost ranks first while browsing the internet. In order to clearly understand working of PageRank, we first need to know the concept of Markov chains. Markov chains consist of mainly of nodes also known as states, and the arrows connecting these nodes to each other also known as links. Now let us consider a user surfing the web network which only consists of these 4 web pages. The surfing of the surfer is random, so in order to predict the next web page, the surfer lands, certain probabilities are assigned to both web pages as well as the links joining these web pages. In this web network, there is a 50% probability for surfer at web page B to land at web page A, and there is a 50% probability for surfer at web page B to land at web page C. Similarly, for a surfer at web page C there is a 100% chance to land on web page D. Now, in this web network, ranks of pages are assigned on how frequent a surfer visits a single web page. This is known as ranking of states. Here, the surfer has visited page B thrice while surfing the web, so it will be ranked highest. But as it can be seen that web pages A and D are visited for same amount by the surfer, this causes a dilemma as to which page should be ranked higher. A proper mathematical way to rank web pages is by developing a stationary Markov chain distribution. A distribution of a Markov chain is said to be stationary if the overall distribution of user surfing through the web network remains constant even though the distribution at each jump from one web page to another is different. For clarity, let us assume that for a job at a company 4 individuals are selected. And these 4 individuals need to decide who is best suited for this job by voting each other, but they cannot vote for themselves, and sum total of all the given votes should be 1. Here, James gives his 1 vote to Sam as a candidate well suited for the job. Sam gives half votes to both Nick and Donald. Nick gives half votes to both James and Donald. And Donald gives his half votes to James and Sam as better suitors. Now, in order to rank among the 4 of the candidates, we treat each individual candidate as a node and their votes to each other as links. We introduce a row probability vector pi k which holds for probability of being in a state at iteration k. Pi k equals pi0, pi1, pi2 and pi3. For the initial state, i.e. pi0, we always consider each state node to be equally likely. We introduce the transition matrix H, whose rows are the current states and columns consist of probabilities of going to next state from that state. The equation for finding the probability of a state after an iteration or transition can be given as a dot product of transpose of transitional matrix and the probability for being in current state, where pi k plus 1 is the probability of new states after a transition. After iteration 1 we see that Sam is ranked topmost, but even though both James and Donald have same number of votes, James is ranked higher and Nick is ranked least. After iteration 2 we see that Sam is still ranked topmost, but both James and Donald are ranked same. And Nick is ranked least. And after many such iterations the ranks of candidates stabilizes and we achieve a stationary distributions. And we see that Sam is ranked topmost, Donald is ranked higher than Sam, and Nick is ranked lowest. Here Sam was ranked higher as James gave his whole 1 vote to him which boosted his rank. Here, Donald was ranked higher than Sam because even though they both had same votes, but as Donald was ranked by Sam whose rank was boosted by James's whole 1 vote, and as he was also give half vote by Nick. While Nick ranked lowest as he was only given a half vote by Sam. Thus, ranks of a web page doesn't only depend on the number web pages it's linked to but to the quality of pages linked to a page. The stationary distribution of this Markov chain corresponds to the properties shown by the eigenvectors. But this is still a half-baked formulation of a PageRank as we didn't consider the stochastic effect. For example, what if a user surfing through a web network jumps to a web pages which has no outlink, then the surfer is stuck there and the stationary distribution gets disturbed. So in order to resolve this issue, a damping factor was introduced in the formulation of PageRank. Here G is the new transition matrix. Alpha is the damping factor. A being a vector of all ones. And A is a column vector with all its elements being 1 for any row with all its elements zeros. Generally alpha is assumed to be 0.85, it means 85% of the time the surfer will browse according to the hyperlink structure, but 15% of times it will go to any random page and start surfing. Thus the final PageRank formula can be given as. Thank you.